Welcome to my Abstract Algebra Final Exam Review Problems and Solutions video. This video is all about the fundamentals of field theory and the basics of Galois theory. It's a pretty tough subject, so we mostly focus on definitions, factual informations, and calculations. Very little in the way of proof. In fact, only in a couple spots I say explain why something happens. That's the only proofs. It's just that challenging of a subject. We talk about vector spaces, dimension, field extensions, splitting fields, algebraic extensions, the degree of an extension, finite fields, and again, the basics of Galois theory. Start with the definition of a vector space. Let F be a field. I'm assuming you know what a field is. Let V be a set that is going to be the vector space, and I will call the elements of V vectors, though you should realize this is not going to be a vector space in the sense that you learn about in physics and linear algebra. This is more abstract. Define what it means for V to be a vector space, and you don't stop there. You should specify what the field is, a vector space over F. A given set V could be a vector space over two or more different fields. That is a possibility, and the behavior of V as a vector space over different fields could be different. What do we want to do to define this? I don't want to do what you might find in a linear algebra book and list about 10 or so properties all out. I want to make use of the fact that in an abstract algebra class, I already know, for example, what an abelian group is. If you don't know what that is, then you wouldn't be taking an abstract algebra class in the final exam for such a course. So I will assume that. So V is going to be a vector space over F if there are two binary operations. There are two binary operations. And by binary operations, at least in the textbook that I use by Joe Gallion, it's assumed that that means closure is satisfied. Satisfying closure. I will put that as an extra comment here, but for my students, that's already part of the definition of a binary operation. Two binary operations that have names called vector addition, where we add two vectors to get another vector. Technically speaking, as a function, you could denote it by plus sign. It takes an ordered pair in the Cartesian product of V with itself and maps it to an element of V. We would denote that kind of mapping by taking the vectors V comma W, that ordered pair, and mapping it to the element written V plus W. And scalar multiplication. Notice that the codomain of this function is V itself. That's why it's closed. Scalar multiplication you should typically denote by what's called juxtaposition. Put the scalar next to the vector. Traditionally, you put the scalar on the left, not on the right. Yeah, we're not going to bother worrying about some sort of commutative property for scalar multiplication, though you could worry about it. We won't. I'm not going to denote it with a dot, but I will write the Cartesian product that is the domain of this function. It's not V cross V, but F cross V. Take a ordered pair that is a scalar, call it A, and a vector, call it V, and map it to a vector that we call AV, which we imagine to be A times V. Okay, that is the nature of that scalar multiplication, such that certain properties hold. The first set of properties, I'm going to save time by just saying that V is an abelian group with respect to addition. If you ignore the scalar multiplication completely, which you certainly can do, V is an abelian group. V is an abelian group under addition, vector addition, this binary operation here. And for the properties related to scalar multiplication, I will actually list them out. Number one, you've got a distributive property. In fact, there's going to be two distributive properties. A scalar A times the sum of two vectors V and W equals A times V plus A times W. For all scalars A in the scalar field F, and for all vectors v and w in the vector space capital V. That is a distributive property. Understand that this means, by putting parentheses around v plus w, that I would do that vector addition first and then multiply by the scalar. And when I write it this way, I do the scalar multiplications first, a times v and a times w, and then add the results. I could put this in the opposite order because v is also an abelian group. That's one distributive property of scalar multiplication over vector addition. There's also a distributive property that you could call scalar multiplication over scalar addition. Two scalars a and b being added and then multiplied times a vector is the same as the first scalar times the vector plus the second scalar times the vector. This is true for all scalars a and b in the scalar field F, and true for all vectors v in the vector space capital V. The third property is an associative property. If you've got two scalars a and b and a vector v, you could do two scalar multiplications like this. Take the vector v and multiply by b first to get a vector bv, and then multiply by the scalar a to get a vector a bv in parentheses. That is the same as multiplying the scalars first before you multiply times the vector. That's also true for all a, b in the scalar field F and all vectors little v in capital V. Final property to write down is that if you take the unity of the field, what's the unity of a field? Well, often it is the number 1, and in general, even in the abstract, we denote it by the symbol representing the number 1 usually. If you take that quantity from the scalar field and multiply times any vector v, you get that vector v. This is an assumption we make when we do the abstract theory of vector spaces over fields. One is assumed to be the unity, the multiplicative identity of the field. Okay? I'm assuming you know what a field is if you are watching this video. On to the second question. Let S be a set of vectors in a vector space V over a field F. Once again, a definition. Define what it means for such a set of vectors to be linearly independent, and again, don't stop there, over the field F, okay? This is always with respect to a field. If I had a different field, it could be a different kind of vector space, and a given set could be linearly independent as a vector space over one field, but perhaps not another. That can happen, okay? So what does this mean? It means whenever you've got a finite set of vectors, v1 through vn, in S, we're talking about S being a linearly independent set over F, and scalars, call them, say, a1 through an, from F, the field of scalars, or the scalar field, whenever this satisfies that a linear combination of them, this kind of quantity here, equals 0, where that's the additive identity of the vector space. Being an abelian group under addition means there would be a 0 and additive identity. Then this implies that all the a's have to be 0. A1, A2 through AN all have to be 0, and that's the 0 in the field. Okay, this is the 0 vector. That's an element of capital V. This is the 0 from the scalar field. This is an element of capital F. Okay? Another way to approach this definition is to first define linear dependence, and then say linear independence is when you're not linearly dependent. And you can define linearly dependent set to say S is linearly dependent over F if there exists some vectors v1 through vn in S and some scalars from F, not all of which are 0, when making this equation true. Okay? Relate this to linear algebra. You can give it geometric meaning. I would encourage you to do so. If you've forgotten, look it up. There's a lot of geometric meaning behind this. Number 3. Let V be a vector space over a field F. Two parts here, and the second part's got a few different parts to it. First, define what it means for a subset B to be a basis for V over F. Secondly, define the dimension of V over F when V has a finite basis over F. And in part B, there's another question. Does this definition require some sort of justification? What does that mean? Do you have to prove the definition? No, definitions aren't proved, but sometimes they need justification, meaning they need to make sense, okay? So we'll talk about that as I go here. So part A, define what it means for B to be a basis for V over F. It means, first of all, B is a linearly independent set over F. B is a linearly independent set over F. B is a subset of V here. That's assumed. I didn't say that. That really is assumed. B is a subset of V. It's got to be a linearly independent set of vectors over F. That's the first condition. Second condition, in linear algebra, you phrase this as B spans V. But what does that mean? It means every element little v of capital V can be written as a linear combination of the elements from B. As V equals A1, I'll go ahead and use the letter, I'll use the letter V's with subscripts. V1 plus A2, V2 plus through AN, VN, some finite linear combination. B could be an infinite set, technically speaking, and S up here could be an infinite set. I forgot to emphasize that. That's possible. But here is a finite linear combination. This is for some A1 through AN in the scalar field, and for some vectors V1 through Vn in the basis B. Okay? A priori, or before the fact, there's nothing about B necessarily being a finite set. B could be an infinite basis. Part B, define the dimension of V over F in the case where V has a finite basis, when B is a finite set. And the answer is the dimension of V over F, sometimes written like this, is the number of elements in the basis. Okay, that's what the definition of the dimension is when V has a finite basis. But wait a minute. Does this require justification? Could a vector space have more than one basis? And could they have a different number of elements? The answer is yes, they could have more than one basis, but no, they can't have a different number of elements, and therefore this definition makes sense. This requires justification. I guess I should have added to this question why or why not. And the justification is that when you've got a finite base, two finite bases, they've got to have the same number of elements. It is justified by the fact, the theorem, that says any two finite bases is the plural basis of a vector space V over a field F have the same number of elements. Are there situations where there are infinite bases or a dimension of a vector space is infinite? Yeah. Okay, we'll talk about that in a bit. Number 4. Let E and F be fields. Define what it means for E to be an extension field of F. What does that mean? You could do a real short definition. You could say E is an extension field of F if F is a subfield of E. You could do that if you've assumed that you've already defined what a subfield is. It's not what our textbook by Galois does. And I think I will go with the way the textbook does it to emphasize something else. So E is an extension field of F if F is a subset of E, and so E is bigger than F. It's an extension of F. And the operations okay, you could phrase this in different ways, of F are the same as E restricted to F. Kind of an odd way to phrase it. And by operations, I mean in a field, not a vector space now. In a field, the operations of addition and multiplication. Not scalar multiplication. I didn't say scalar. I said the operations of addition and multiplication in the field are the same. Okay? This is very much related to the definition of a subfield. We could also say E is an extension field of F if F is a subfield of E, which also means F is a subset of E, and yes, the operations of F are the same as E restricted to F. It's the exact same definition, effectively. If you wanted to visualize this, E is a bigger field than F. Field theory is full of content about field extensions, whereas with groups, it's the opposite. You think about subgroups. So with groups, you start with a bigger group and you think about smaller groups to help you understand the bigger group. With field theory, you start with a smaller field and then you create a bigger field to help you understand, well, connections between the two, and especially in relationship to polynomials and factoring, as we will see. Page 2, we start with a problem that says, state the fundamental theorem of field theory, also called Kroneker's theorem, and also, based on the proof, describe the field that is constructed in that proof of the fundamental theorem of field theory. First of all, what does the fundamental theorem of field theory say? Let F be a field, and here we go with polynomials, let little f of x be a polynomial in the polynomial ring, capital F square bracket x. This is the polynomial ring, or ring of polynomials, all polynomials that you can create with coefficients coming from a field under ordinary polynomial multiplication and addition. It is a ring, not a field, this thing here. You can't invert elements except for the non-zero constant polynomials. Little f of x is a polynomial with coefficients from that. If, for example, f happened to be a finite field like z2 or z3, say to z2, when you multiply and add the polynomials, you have to mod the coefficients by 2 in that case, or 3 if we were talking about z3. So let f be a field and let little f of x be a polynomial in this polynomial ring that is non-constant. So we don't want to talk about constant polynomials here. The conclusion is then there exists an extension field E of f in which the polynomial little f of x has a 0. Or you could say has a root, if you prefer. Having a 0 means for that element, call it little a in capital E, f of a equals 0 when you replace x, the variable, so to speak, or the indeterminate, with the element little a from capital A, E, and do the corresponding operations that have coefficients from f, you get 0. Okay? So that's the statement. What is the field that is constructed in the proof? The field extension E is what I'm referring to. You've got to use f in some way. And the answer, if you study the proof, is that E, the field extension that is constructed, is a certain field that is constructed as a factor ring or quotient ring if you have a different book than Galois. And it's this quotient ring or factor ring. Take the ring of polynomials with coefficients from f and mod out by the principal ideal generated by little f of x. Excuse me, that's wrong. Little p of x where little p of x is a factor of little f of x that is irreducible over the base field f. Okay, that's a p of x. Little f of x may or may not be irreducible. You might be able to factor it. You might not be able to. If little f of x is already irreducible, if you can't factor it over f, then you can use f of x here. But we want, if little f of x is not irreducible, if you can factor it, we want to have an irreducible polynomial there because knowledge about rings here, that makes this principal ideal generated by the irreducible polynomial a maximal ideal in this polynomial ring. And when that's a maximal ideal, it makes this factor ring or quotient ring actually a field. Okay? If you've not studied this, you probably have no idea what I'm talking about at all. I'm assuming you've done some studying here. I probably should mention that it seems a little odd to call E a field extension of f here because, well, the elements of f are just arbitrary symbols, you might say. They could be numbers, whereas the elements of E are evidently cosets in a factor ring. So how could this be an extension of that? And the answer is you essentially associated cosets with a constant representative, a plus the ideal, get associated with the corresponding element in the base field f. You think of that coset as being equivalent or the same as the corresponding element that is the representative in front of the coset from the field f. That's the way you make the association to say you can think of this as a field extension of f or f as a subfield of E. In fact, all the cosets that can be written like this, where a is a constant polynomial, effectively an element of f, is a subfield of E that is isomorphic to f. Number 6. Let f be a field, the base field again. Let a1 through an be elements in some extension field of E of f. Define or describe what this symbol represents. This is a big deal. Might not seem like a big deal, but it is a big deal. What does this symbol represent? Okay, I always draw this picture here. Here's f. Here's E. Where are these a's? They are in E. Technically speaking, some of them could also be in f because f is a subfield of E. There are the a's. What does this symbol represent? This is a standard symbol to represent the smallest subfield of E containing all of f and also containing all these elements a1 through an. Now I'm kind of going to draw it, but you kind of got to take the drawing with, what's the phrase? A grain of salt, right? Don't take it too literally. I'm just trying to draw it in such a way that that helps you understand the definition, you might say. What does this represent? It represents the smallest, like I said verbally, the smallest subfield of E containing f as a subfield of this. This thing is going to be a field by definition. It contains f and containing these elements a1 through an. It's called f adjoin a1 through an, but it's easy to misinterpret what that means. It does not mean take f and just its union with the set of these n elements. It does not mean that. Okay? That would not be big enough. You might say you want this thing to be a field, and so it contains more than just f in these n elements. It also, for example, contains the powers of these n elements, and when you add these elements to themselves, multiply them by scalars, which means, like 2a1 would really mean a1 plus a1. It's got to contain all those things too, because it's still got to be a field. So it contains, yes, f and a1 through an, but it contains a lot more that wasn't originally in f, at least if these a's, if some of them are not in f to begin with. Okay? Very important concept we're going to make use of here. Number 7. Let E be an extension field of f, and let little f of x in this polynomial ring with coefficients from capital F, the base field, have degree at least 1, so it's not a constant polynomial. Define what it means for little f of x to split in E, and then define what it means for E to be a splitting field for little f of x over capital F. Then a final question, do splitting fields always exist? Just a knowledge question. Is there a theorem related to that fact or not? This always kind of gave me nightmares, splitting fields. It's a pretty difficult concept, to me at least. When I was first learning it, it's less difficult now. What does it, first of all, mean for f of x to split in E? It means there exists, well, first of all, what you might call a leading coefficient, a, from the base field f, as well as some other quantities, symbols, from the extension field E. I meant to put an a in here. Such that f of x is factorable in the following way. F of x can be factored as a times x minus a1 times x minus a2 through x minus an. Technically speaking, you would think of this as a factorization in the polynomial ring E square bracket x, because these a's could be in E and they also could possibly not be in f. I mean, some of them might be in f, but some of them might not be, or they might all not be in f. So that's what it means to split. You can completely factor it in terms of linear factors with a coefficient a of ultimately the highest power of x that is from the base field f. Based on this definition, then define what it means for E to be a splitting field of f, little f of x over f. It means not only does little f of x split in E, but also E is the smallest subfield of some bigger field, perhaps, in which little f of x splits. E equals f adjoin a1 through an, which again does not mean just take f and union it with this set. It means more than that. It is the smallest subfield of E containing f and containing these elements. We are sort of implicitly assuming here, based on this definition, that there's an even bigger field in which E sits, to say this. A splitting field, you might say, is a minimal field extension in which the polynomial splits. Number 8. Let f be a field and let a be an element of some extension field E of f. 4 parts. Define what it means for a to be algebraic over f. What do we call a if it's not algebraic over f? What does it mean for E to be an algebraic extension of f? And something not really related to this so much, the algebraic, is what does it mean for a to be, or no, I should say for E. What does it mean for E to be a simple extension of f? That's a typo there. Okay? A, what does it mean for a to be algebraic over f? This is a very important definition historically. It's a big part of the motivation for studying field theory and field extensions here in part A. A is algebraic over F if A is a zero, a root, of some polynomial with coefficients from F. A is a zero of some little f of x in the polynomial ring capital F of square bracket x, meaning polynomials with coefficients from F. That's what it means to be algebraic over F. What does it mean if A is not algebraic over F? What do we call it? Then we call A transcendental over F when that doesn't happen. Which brings up a question. Are there examples of transcendental elements? And we will see on the next page that there are. That's very, very important historically. I think I read Euler came up with transcendental as the name for non-algebraic elements. They transcend algebra. That's why he used the term. C, what does it mean for E to be an algebraic extension of F? Not an algebraic element, but an algebraic extension. It means all elements of E are algebraic over F. By the way, all elements of the base field will be algebraic over the base field. If B is an element of the base field, it's going to be algebraic over the base field because it's going to be a zero of x minus b in this polynomial ring, a linear polynomial. I didn't ask for it here, but I could have also asked, what does it mean to be a transcendental extension? To be a transcendental extension means there's at least one element that's not algebraic. There's at least one element that's transcendental over F. Part D, what does it mean for E to be a simple extension of F? It means E equals F adjoin some element, a single element, meaning, again, not meaning F union with that element. It means the smallest subfield of some bigger field containing all of F and containing A, which also contain A squared, A cubed, A plus A, A plus A plus A, negative A inverse. Negative A is the additive inverse of A inverse is the multiplicative inverse of A, assuming A is non-zero. That's what it means to be a simple extension. Third page is some more statements and definitions, as well as some true-false. Then into the fourth page after that, we get onto some calculations and some, well, maybe not full proofs, but at least explanations. Number 9 says, state the classification theorem for finite fields first. And part B, state the structure theorem of finite fields. The classification theorem of finite fields says that for every prime p and every positive integer n, so p is 2 or 3 or 5 or 7 or 11 or 13 or 17, etc. n is 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8, etc. There exists up to isomorphism. I'll explain what that means in a second. Up to isomorphism, a unique field of order p to the n, having p to the n elements. Only a single one. We denote it by GF p to the n. G means Galois, in honor of a person whose last name was Galois, a French person. Galois field of order p to the n. What does unique up to isomorphism mean? Well, technically speaking, you could have two quote-unquote different fields, different because they're constructed in different ways, perhaps, and have different elements and different operations, that are really the same because they're isomorphic to each other. That's what up to isomorphism means. And with that condition, up to isomorphism, it's a unique field of order p to the n. Part B, related to this notation, says as a group under addition, fields have addition and multiplication. They're not the same as vector spaces, though I should mention, and this is going to come up, all vector spaces, or all fields are vector spaces over subfields. I'll mention that again. But in general, when you're thinking about field theory, you're not thinking about vector spaces. You've got an addition and a multiplication. As a group under addition, GF p to the n is isomorphic to the external direct product of ZP with itself, where you've got n factors, n of those ZPs, n copies. External direct products like this, technically speaking, are defined to be, in this case, ordered n tuples, where in this case the addition would be done component-wise, just like with vectors. And as a group under multiplication, GFPN star, which really represents the field take away 0, is cyclic. And if you take away the one element 0 from this group of order p to the n, it's going to have p to the n minus 1 elements. And to be cyclic means it's going to be isomorphic to z sub p to the n minus 1. Notice the minus 1 is here, not up in the exponent. So for example, if p is 3 and n is 4, 3 to the 4th is 81. Galois field of order 81 is isomorphic to 4 copies of z3 being producted with each other. Made up a word there. As a group under multiplication, the Galois field of order 81, meaning take away 0, is going to have 80 elements, will be isomorphic to z sub 80. As a group under multiplication, it'll be cyclic. Okay, that's what that theorem says. Number 10, let E be an extension field of F. Oh, here's the basics of Galois theory. Part A, define what the Galois group, gal of E over F, don't think of this as a quotient ring or anything. It's not. It's just notation. The Galois group, not ring, not field, Galois group, gal of E over F, define what that is by describing its elements and its binary operation. It is a group. It's got some elements. It's got a certain binary operation. Part B, describe the element that acts as the identity element of the group. Part C, if H is a subgroup of the Galois group, define what's called the fixed field E sub H of H. So what is this? Okay, you've learned Galois theory or not, so you're either reviewing it or you're learning this for the first time. E is an extension field of F. You could make a drawing like this. It's also common to make a tower of fields, or you could call it a lattice of fields, where the smaller field is below the bigger one. What is the Galois group? As a set, it's the set, I'll just describe this in words. Of all field, you could use either the word isomorphism or automorphism. It's more traditional to use automorphism. If you use the word isomorphism, you'd have to be more explicit about what the domain and codomain of these things are. By automorphism, I automatically mean from, ultimately here, it's going to be e to itself, I'll write that like this. These are going to be isomorphisms. In fact, you could call them ring isomorphisms from e to itself. And by ring isomorphism, I mean they preserve addition and multiplication. They're going to be one-to-one and onto as well. And because it goes from e to itself, you typically use the word auto instead of iso. Okay? Field automorphisms from e to itself that have an additional property that, quote unquote, fix elements of the base field F. Or for short, they fix F. Well, what does that mean? So I'm kind of not really giving an official definition here in a traditional sense. I.e., say phi of x equals x for all x in capital F and for all phi in the Galois group of E over F. And we should describe the binary operation. Well, the elements of this Galois group are functions, automorphisms. The only thing that makes sense, no, you could make sense of other things, but the group operation is function composition. The binary operation is function composition. Being one-to-one and onto functions from e to itself, you could also call them permutations of e. But they are also operation preserving, doubly so, preserving both addition and multiplication. But you'll see when you get into Galois theory that you typically think about how the elements of the Galois group permute roots of polynomials. And so in that sense, you do think of them as permutations. And Galois thought of them that way. And that was kind of, the origins of group theory was actually with permutations, when Galois was thinking about this stuff back in the early 1800s. What element acts as the identity? Part B. It would be the identity mapping, epsilon, from E to E, defined by the formula epsilon of x equals x for all x in E, not F, or for all x in E. This was an all x in F over here. Certainly, this thing will be doubly operation preserve addition and multiplication. That's easy to check. Certainly, it's one-to-one and onto. It maps from E to itself. And certainly, it fixes all of F, the smaller field, because it fixes everything in E. And if you compose it with any other such function, you'll get that other function. Under function composition, this will be the identity. Part C, if H is a subgroup of the Galois group, define the fixed field E sub H of H. It's, in general, going to be a field in between, you might say, F and H, or F and E. E sub H is going to be a field, in general, between F and E. It's a subfield of E. It's a field extension of F. It's the set of everything in E that gets mapped to itself under elements of H, satisfying the property that phi of x equals x for all phi in H. H is a subgroup of the Galois group. Its elements are field automorphisms from E to itself that fix elements of F. E sub H, if H is a subgroup of the Galois group, is going to fix all elements of the fixed field, as phi varies over H. Okay, so this is going to be a subgroup of the Galois group, because if they fix elements of the fixed field, they're also going to fix elements of F. last page, we get into an example. Hang on for that. Bunch of true-false questions. I'll go through pretty quickly here. Number 11 is historical importance. It says the number pi is algebraic over Q. No. False. Pi, the special number pi, is most definitely transcendental over Q. It is not a zero of any polynomial with coefficients in Q, the rationals. Okay? That is historically, in the history of math, a super important thing. Somebody finally proved the existence of a transcendental number. I do believe pi was the first one to be proved to be transcendental. It's actually easy to prove transcendental numbers exist using a counting argument, and the fact that the algebraic numbers in the real numbers are what's called a countable set, but the real numbers are uncountable, and that means transcendental numbers definitely have to exist, and in fact most real numbers are transcendental over the rationals. But proving any particular number is transcendental is very, very difficult. Historically, this is very important. If that word were transcendental, then that would be true. True or false, if K is a finite extension field of E is a finite extension field of F, and K is a finite extension field of F. Let's see. K is of E is of F, then K is a finite extension field of F. Okay, so I kind of messed up in describing this here. So F is the lowest field in the lattice here. E is in between, and K is the highest one. I haven't defined what finite extension means. I probably should have done that. It does not mean that it's a finite set. Okay, it does not mean that. It means the dimension of K as a vector space over E is finite. The dimension E is a finite extension of F. The dimension of E as a vector space over F is finite. You know, 10, 15 minutes ago or something I mentioned, fields are always vector spaces over subfields. Dimension is the number of elements in any basis. If there's no finite basis, it does mean it's an infinite dimensional vector space. Finite extension means it's a finite dimensional vector space. There's a finite basis. If these are both finite extensions in this diagram, then the biggest field is also a finite extension of the lowest field, the smallest. That is true. It's a theorem. And this equality is true. And what do these symbols mean? I haven't explained that either. For example, this symbol here is, by definition, what's called the degree of K over F. That symbol shows up right there. And by definition, it's the dimension of K as a vector space over F. This is true. Okay, and it's a pretty useful fact in advanced field theory. True or false, the field with 8 elements has a subfield with 4 elements. Galois field of order 8, which is 2 cubed, has a subfield of order 4, which is 2 squared. You might think that since 4 divides 8, the answer is true. But actually the answer is false. Because you don't look at the orders of the fields themselves and ask whether that one divides that one. You ask, first of all, are their bases the same? In this case, of the number of elements, 2, yes, they are the same. And if they are the same, you ask whether the power of the smaller one divides the power of the bigger one. 2 does not divide 3. And because of that, it turns out no. A field of order 8 does not have a subfield of order 4. It would have a subfield of order 2, 2 to the first. 1 divides 3. So it would have a subfield of order 2, but not a subfield of order 4. If, on the other hand, I've made this G16 instead of G8, GF16, 16 is 2 to the fourth instead of 2 cubed. 2 does divide 4, so GF16, Galois field of order 16, does have a subfield of order 4, as well as a subfield of order 1 of order 2. You got to look. First, are the bases the same, the primes? Secondly, if they are, then you look at the exponents does the smaller exponent divide the larger exponent or not? If it does not, then the answer is no, it's no subfield. If it does, then there is a subfield. True or false, ZP is a field for any prime P. That's true. It's just a fact to know. And in fact, you could say GFP is isomorphic to ZP. And that's got to be the case. A prime to the first power is just a prime. True or false, the only ideals in a field are the trivial one and the field itself. That's true. I did that actually on my exam 3 review, and I even proved it. Maybe it doesn't really fit so much on this exam, but I wanted to remind people of it anyway. With fields, the concept of ideals and subfields are really different. Ideals are special kind of subrings. And these are subrings of the field F, and they are ideals, but there's no other ideals in a field, but there are other subfields. So it's a little confusing, and subfields are also subrings. Wow, that's a confusing thing to think about, but I'll go ahead and let you think about it. 16 is also historically important. There exists a quintic polynomial, 5th degree, with coefficients from the rationals that is not solvable by radicals, meaning essentially there's no generalization of the quadratic formula for solving a general 5th degree polynomial, and maybe to prove that, just find one example. And historically, you should know the answer to this is true. Okay, and it's part of the purpose of Galois theory, and in Gallien's book, in the chapter about Galois theory, it's proved at the very end, though for my students, we always run out of time at the end of the semester and we don't get to that proof, and it's just very hard, and we're trying to just do the basics of field theory and Galois theory. 17, if E is an algebraic extension field of F, then E is a finite extension field. In other words, if every element of E is algebraic over F, the root of some polynomial with coefficients in F, then E as a vector space over F has a finite dimension. The answer to that is actually false. As an example, C, for example, the complex number, is algebraic over Q. Algebraic over Q, the rationals, but not finite. It's not a finite dimensional vector space over Q. It is a finite dimensional vector space over the real numbers, but not the rational numbers. I'll let you think about that. If I reversed this, if I looked at the converse of this, that actually would be true. If E is a finite extension, then it's also algebraic. There's a theorem that says that's true. But this statement is false. 2 more pages, more calculational in nature. And this one, 19, does involve an explanation that I could have called a proof. Let's look at 18 first. Find the splitting field of this polynomial over Q. Express your answer as a simple extension, Q of A for some element A. Now, there are plenty of problems you can create that are like this that are much harder. This one's relatively easy. And in fact, I've helped my students to factor this by doing this. And this is true, right? Because out of the first 2 terms, there's a common factor of x squared that can be factored out. And out of this last 2 terms, there's effectively a 1 that can be factored out. And I'm putting parentheses there to let you know that then, oh, you could factor this more. You could factor the x minus 1 out and get x squared plus 1 times x minus 1. So this polynomial is reducible over Q, because I can factor it in terms of lower degree polynomials. I'm after the splitting field of it, meaning I'm after the smallest field extension of Q, or the smallest subfield of C, that contains all of Q and also the roots. Pretty clearly you can see by this factorization that the zeros, or roots, of this little f of x are 1, I, and negative I, where of course I is the imaginary unit, I squared is negative 1, and by the way, that also means negative I squared is negative 1. And so you could say the splitting field E is this. You could write it this way. But the goal is to express the answer in this form. This is the smallest subfield of the complex numbers containing all the rationals, containing 1, containing I, containing negative I. 1's already a rational, so for sure I don't have to put that there inside the parentheses. You might hope that with I and negative I, you could get away with just putting I, for example, or negative I. And I'm saying just give the answer, so if a student just wrote that and circled it, they get full credit. If I ask them to explain, they should be able to. I will just do it verbally here. Why are these equal? It's always tricky. Think with me here. This is the smallest subfield of the complex numbers containing all the rational numbers and I. Again, that does not mean it's the rationals union with the one element set I. It will contain, for example, 2I and 3I and negative I and negative 2I and even rational multiples of that, 5/3 I, for example. It also contains I squared, although that's negative 1, which is already rational. This is the smallest subfield of the complex numbers containing all the rationals 1, I, and negative I. Since that's the smallest one containing all the rationals and I, and this one does contain I, this one's got to be quote-unquote bigger than this one, or equal to it. That proves, verbally, this inclusion, that this is a subset of that. It does end up being equal to it, though. What proves the other inclusion, that this is a subset of that? If I can verify that each element over here is in there, that's enough. Why? Because this is the smallest subfield of the complex numbers containing, for example, I. If this one also contains I, this one's got to be quote-unquote bigger or equal. This is the smallest subfield of the rationals containing Q, 1, I, and negative I. It does contain negative I. If this one contains negative I, it's got to be bigger again or equal. And same kind of thing with 1. Obviously, this contains 1. Obviously, it contains I. And almost obviously, it contains negative I. Why? Well, it contains an I, and therefore it's got to contain its additive inverse because it is a field by definition. It's got to contain negative I too. So I'm not writing it out. I'm just verbally saying it. Maybe your teacher will ask you to write it out. 19. This is effectively our only proof in this test, although there's a short explanation in the next problem, or next page. Explain why or prove this equality. There's a note here. Why is that there? Must be helpful. Okay, how do you do this? In this kind of situation, the inclusion from a simple extension to a non-simple extension, this inclusion is easier to prove. This is our first case. So let's explain or effectively prove. And just like up here in the previous problem, because we got q's in the front, it's enough to just prove that this thing, square root of 2 plus square root of 3, that's in here by definition, is also in there. Because by definition, this is the smallest subfield of C containing all the rationals and this thing. If this thing is in here, this thing's got to be quote-unquote bigger or equal. Get that? Let's write it out. And why is this thing in there? It's based on this being a field, and because square root of 2 and square root of 3 individually are in there. By definition, square root of 2 and square root of 3 individually are in the one on the left, which, by the way, this is worth mentioning. It's not part of this problem, but it's worth mentioning. This does equal Q adjoin root 2, that field, then adjoin root 3, which also equals Q adjoin root 3, take that field and adjoin root 2. Okay, I said that kind of quick. Let you think about that. It's not really part of the problem, but it's just an extra side comment here. By definition, these things are in here, and this thing, by definition, is a field. By definition of the symbol. It's a subfield of the complex numbers. Subfield of real numbers, even. Therefore, 3 dots means therefore square root of 2 plus square root of 3 is also in here by closure under addition. That proves Q adjoin root 2 plus root 3, the simple extension, is a subset or subfield of the other one. I switched around the order here. The harder inclusion to prove is this one. But once again, if I can prove square root of 2 and square root of 3 individually, which by definition are in here, are also in here, then I'll be done. Because this is, by definition, the smallest subfield of C containing all the rationals, also containing root 2 and root 3. Therefore, if they're both in here, this one has to be bigger or equal. The note, the hint, is really a hint that's supposed to help you figure out how to prove that square root of 2 and square root of 3 individually are in here. How so? Well, maybe first you should verify that this hint is really true. If a is square root of 2 plus square root of 3 is its multiplicative inverse, 1 over a to the negative 1 power, really equal to square root of 3 minus square root of 2. Well, you could just multiply these things and see that you get 1. Foil them. First times first is square root of 6. Outside times outside is minus 2. Let me go ahead and do that. Multiply. Square root of 2 times square root of 3 is square root of 6. Outside times outside is minus 2. Inside times inside is plus 3. Last times last is negative square root of 6. Those cancel, and then negative 2 plus 3 is 1. You also could get from here to here by like a rationalizing the denominator kind of thing. Multiply the top and the bottom by square root of 2 minus square root of 3. Sorry that I'm writing over the other one. And you get this. This is supposed to be a square root of 3 minus square root of 2. How is that helpful, though? Think about this. Notice something. If you added a and 1 over a, the square root of 2's would cancel. Note a plus 1 over a is square root of 2 plus square root of 3 plus square root of 3 minus square root of 2. The square root of 2's cancel, leaving you with 2 root 3. So root 3 is 1/2 times a plus 1 over a. A is this. I should have maybe said that down here. A is this. A is definitely in here, and this is a field. Therefore, 1 over a is definitely in here. A is also non-zero. And 1/2 times their sum. Well, their sum is also in there, and 1/2 times it's also in there. It's a field. Those things have to be in there. And 1/2 is a rational number. So the point of all of this is this means that this is an element of the field on the right. Okay? It's for sure an element of the field on the left by definition, and because of these calculations, it's also an element of the field on the right. And so that's what, when you add them, the square root of 2's cancel. When you subtract a minus 1 over a, the square root of 3's cancel. A minus 1 over a, square root of 2 plus square root of 3 minus square root of 3 minus square root of 2. The square root of 3's cancel, leaving you with 2 square root of 2. So square root of 2 is 1/2 times, in parentheses, a minus 1 over a. Same argument then allows you to say that square root of 2 is in here. Again, this thing is the a, so it's in there. Its multiplicative inverse, 1 over a, is in this because it's a field. And if I add them or subtract them, it'll still be in here by closure as well. Multiply by 1/2, it's still going to be in there as well. And that's enough. Therefore, this proves this inclusion. Once again, the reason you could give, it's really by definition of these symbols. I just showed square root of 2 and square root of 3, which by definition are in here, are also in here. This is by definition the smallest subfield of the complex numbers containing square root of 2 and square root of 3 and the rationals. This contains the rationals and those things, so it's got to be quote unquote bigger or equal. And ultimately they're equal, because I've shown both inclusions. Therefore, these things are equal. Pretty fundamental kind of argument in the theory of fields and their extensions to be able to do this. 20. Consider this cubic in this polynomial ring. So I'm assuming the coefficients are from z2, meaning either 0 or 1. And when I add polynomials or multiply them, I got to mod the coefficients by 2. Let beta be a 0 of f of x in some extension field E of z2. Such a 0 will exist by the fundamental theorem of field theory, Kroneker's theorem. Do I need to write it as a coset, as in the proof of that theorem? No, you don't have to. We could just write it as a pure symbol, beta. Beta could be a coset of a factor ring, that's a field, but it doesn't have to be thought of that way. I'm telling you, it turns out that beta squared is 0 as well, and we'll check that actually as we do this problem. Use either long division or synthetic division to find the third 0 of f of x and e. And in so doing, we will also confirm beta squared is a 0. Though, by me telling you that, it will help you find the third 0. After you've found the third 0, then you can easily write f of x as a product of linear factors in this polynomial ring. Long division is fine. I prefer using the synthetic division. When you're dividing by linear polynomials, you can use synthetic division. If you're, for example, dividing by x minus beta, which since the coefficients are modded by 2 is the same as x plus beta, you put the beta over here, and underneath this bar here you put the coefficients of f, including any that are missing. Make sure to put a 0 if it's missing. So the coefficient of x cubed is 1. Coefficient of x squared is 0. That needs to be put in there. The coefficient of x is 1, and the constant term is 1. By the way, this is another big kind of problem that I had difficulty with when I was first learning this material. And I didn't realize you could use synthetic division to do this kind of stuff, and a teacher really helped me by saying, hey, why don't you just use synthetic division? It makes things so much simpler. I didn't really know what to do. I was really just focused on memorizing theorems and definitions and stuff. I didn't have the practical knowledge of how to do computations on all this. So with synthetic division, you take the first number and bring it down there. Then you multiply. Beta times 1 will be beta. Then you add 0 plus beta is beta in this field extension E that I'm not specifying what it is. E of z2. Multiply beta times beta is, well, you could call it beta squared. Add beta squared plus 1 can be written like this. Multiply beta times beta squared plus 1 is beta cubed plus beta. Add beta cubed plus beta plus 1. And if it's beta is a 0 of this polynomial, make a line there, this is supposed to be 0. So it should get a remainder of 0 when you divide this polynomial by x minus beta. Is that 0? It doesn't look like 0. It's 0 by assumption. Beta is a 0 of f of x. That's f of beta. It equals 0 by assumption. I mean, yes, you need to prove beta exists. That's done, again, with the fundamental theorem of field theory, Kroneker's theorem. There's an extension field in which f of x has a 0. Call it beta. All right. And when you divide f of x by x minus beta, which again is the same as x plus beta because the coefficients are mod 2, the quadratic that you're left over with as a quotient will have these coefficients. So it'll be x squared plus beta times x plus this quantity, beta squared plus 1 in parentheses, times x to the 0, which is just 1. So I guess you don't need it in parentheses. That's the constant term. I claim beta squared is another 0. So if I once again do a synthetic division like this, another nice thing about synthetic division is you can stack these things on top of each other. I should get 0 for the remainder here as well. Bring down the 1, multiply, add, multiply beta squared times this, put it there, you get beta to the 4th plus beta cubed, add beta to the 4th plus beta cubed plus beta squared plus 1. I like putting a vertical line here. That's the remainder. Doesn't look like it's 0, does it? But you can simplify it to see it's 0, it turns out. Beta cubed plus beta plus 1 equaling 0 means beta cubed can also be thought of as negative beta, the additive inverse of beta, minus 1, the additive inverse of 1, which, since coefficients are mod 2, is the same as beta plus 1, mod 2. And that will also mean beta to the 4th will be beta squared plus beta. Multiply each of those by beta. Substitute everything. Beta to the 4th is beta squared plus beta. Beta cubed is beta plus 1. And then we have beta squared plus 1. So you got 2 beta squared plus 2 beta plus 2. But that's 0 mod 2. The coefficients get modded by 2. That's the way this works for this kind of example when the base field is Z2. And the extension field, you still mod the coefficients by 2. And this is the coefficients of the linear polynomial that's left. So this means I found the third 0. The third 0 is the 0 of, look at the coefficients here, x plus beta squared plus beta, which you could call negative beta squared minus beta, but mod the coefficients by 2. That's the same as beta squared plus beta, mod 2. And all this ultimately means, there's the answer. So this was part A so far. Part B, f of x can be factored as, I could use minus signs or plus signs. X minus beta times x minus beta squared times x minus, in parentheses, beta squared plus beta. Or again, since it's mod 2 arithmetic, this is the same as x plus beta times x plus beta squared times x plus beta squared plus beta. It would be a good exercise for you to expand this out, multiply it all out, simplify, using the fact that these things are true up here, to see that you get the original polynomial, x cubed plus x plus 1. Don't forget to mod the coefficients by 2. Okay, with my students, I do lots of these kind of examples in class. Last page. A pretty long problem, and then a fairly short problem related to Galois theory. Yikes, look at that polynomial. Let f of x be, whoa, this big long 6-degree polynomial with coefficients from the integers, and all integers are rational numbers, so I can think of it as being in either polynomial ring. If you think of it as being in this one, and notice that all those coefficients except the first one are divisible by 3, and the constant term is not divisible by 3 squared, note that this is irreducible over Q by Eisenstein's criterion with the prime equal to 3. Okay, you got to know what Eisenstein's criterion is. I'm just telling my students that to help them finish the problem. Part A, what kind of ideal is this principal ideal in this ring? Since this is irreducible, there's a theorem that says this principal ideal will be maximal. It's a maximal ideal in here. That's going to be related to a certain factor ring that I could create, also called the quotient ring. B, let A be a 0 of f of x in some extension field of Q, which will exist by the fundamental theorem of field theory. It also exists by the fundamental theorem of algebra. It's going to be well, it could be a real non-rational number. It also could be, in general, a complex number. What factor ring is Q of A, Q adjoin A, isomorphic to? So here I'm thinking most typically at least, of A being a non-rational real number or a complex non-real number. That's the typical way to imagine this, but I'm saying it's also isomorphic to a factor ring, so the extension field could be constructed as a factor ring, as in the proof of the fundamental theorem of field theory. And that's essentially what this is going to be isomorphic to. Q of A is isomorphic to this factor ring. Take the polynomial ring Qx and mod by the ideal. The principal ideal generated by this irreducible polynomial, that essentially is in the proof of Kroneker's theorem, fundamental theorem of field theory. It's also just a fact you could say in general. C, describe what the elements of Q of A look like in terms of A. Factual information to know. This is a very useful fact. This is one of the most useful facts in this subject. As a set, since A is a 0 of f of x, which is irreducible over Q, that means every element here turns out to be a linear combination of powers of A, starting with the 0th power and going through a power equal to the degree of f of x minus 1, the 5th power in this case. Doesn't matter what order you write them in. You could write, say, C5 a to the 5th plus C4 a to the 4th plus C3 a cubed plus C2 a squared plus C1a plus C0 times 1, which you could just write as C0, where each of these CI's is in the base field Q. For I goes from 0 to 5. That's a theorem. Okay? That's what how this set can be described in terms of A, in terms of powers of A. And it's related, the 5 there, the highest power, is related to the fact that this f of x has degree 6 and is irreducible over Q. So this power here, that's the highest power of A, is always n minus 1, where n is the degree of the irreducible polynomial you're working with. Part D, write down a basis for Q of A as a vector space over the smaller field Q. Effectively, it's this theorem with a little extra. What this equality here is saying is the powers of A, starting with a to the 0, then getting up to a to the 5th, do span Q of A. Every element of Q of A can be written as a linear combination like this. In Gallien's book, it also says that representation is unique. The C's are unique. And that effectively means that the powers of A are linearly independent as well. So the basis consists of those powers of A, starting with the 0th power, which is 1, and ending with the 5th power. So you've got 6 elements in a basis. And that means the answer for part E, the degree, is also 6. This is the dimension of the vector space, Q of A as a vector space over Q. That's going to be 6 by part D. There's 6 elements in that basis. Part F is Q of A, a finite extension of Q. Why? Yes, because this degree is finite. Part G. All right, here's a little Galois theory. What is the order of the Galois group? You got to know the fundamental theorem of Galois theory here, not just the definition of the Galois group. Fundamental theorem of Galois theory implies that the order of the Galois group of Q of A over Q is the same as the index of Q of A over Q, which is 6. So the Galois group as a group has order 6. There's 6 elements. So part G, what possible isomorphism classes are there for the Galois group? Then you got to know a theorem about classifying finite groups. I guess that's part H. Sorry, that's a typo. Part H, what are the possible isomorphism classes? Since the Galois group has order 6, you got to know how to classify groups of order 6. And there's only 2 possibilities. Groups of order 6 are either isomorphic to Z6, meaning they're cyclic, or there's 2 ways this is typically written. S3, the symmetric group on 3 objects. I also could use, this is isomorphic to another group we call D3, the dihedral group, which is the symmetries of an equilateral triangle. So either writing Z6 or S3 or writing Z6 or D3 is correct because these 2 things are isomorphic. Up to isomorphism, there's only 2 groups of order 6. So those are the possible isomorphism classes of the Galois group. To figure out which one it is, well, this is abelian, this one's not, so you could see if the Galois group happens to be abelian or not. Or you could, if you suspect it's Z6, you could try to find a generator. I am keeping this exam at the real basics of Galois theory, so I'm not actually trying to find the Galois group here. I will say before I go into the next problem that writing Q of A in this way is helpful. And also realizing elements of the Galois group do have to permute. I mentioned this maybe an hour ago. Permute roots of this polynomial in this field extension here. By the way, the fundamental theorem of Galois theory does only apply to field extensions that are splitting fields of some polynomial, as this one is. Q of A is this, well, it's a splitting field. Yeah, it would have to be for this irreducible polynomial. So yeah. And it's going to permute the roots. Conceivably, those roots could include complex numbers that are not real. Conceivably, they could all be real and just irrational. But either way, it's got to be one of these 2 things. The reason that they permute the roots is because if you apply an automorphism to this polynomial, assuming you've plugged in a root, a 0, you'll get that the output of the automorphism also has to be a root, a 0, using operation preserving properties. And you'll also see that it fixes all rational numbers as well. Last problem. If in a certain situation the Galois group happened to be isomorphic to Z6, The question is, how many subfields are there of the field Q of A that contain Q, including Q of A and Q themselves? Show your work, briefly explain. This is really the fundamental theorem of Galois theory as well. And what you want to do to answer it is realize that the theorem, though I won't state it because it's very complicated, essentially gives a nice correspondence between subgroup lattices for the Galois group and tower of fields or lattice of fields, subfields of Q of A. Subgroup lattice for Z6. Z6 is cyclic. It's going to be on top. It's got 1 as a generator, for example. 5 is also a generator. By the way the operation here as a group is just addition mod 6, not multiplication. The fundamental theorem of cyclic groups says that for each divisor of 6, the order of this group, there's got to be exactly one subgroup. The divisors of 6 are 1, 2, 3, and 6. Z6 itself is a subgroup of order 6. Trivial subgroup, just 0, is a subgroup of order 1 that would have index 6 in Z6. And there would be a subgroup of order 2 and a subgroup of order 3. The subgroup of order 3 is, order 2, is generated by 3, just 0 and 3. And the subgroup of order 3 is generated by 2, and also 4, contains 0, 2, and 4. And I'm putting them next to each other, though maybe I should put this one a little higher since it's bigger, because neither one is a subgroup of the other. So the subgroup lattice effectively looks like this. And sometimes in Galois theory, you label these lines with the indices. This trivial one has index 2 in this subgroup, and index 3 in this one. Indices of groups meaning number of cosets. This one's got index 3 in the entire group, and this one's got index 2 in the entire group. The lattice, corresponding lattice of subfields, I'm not going to completely specify, but it does effectively match what you see here. Let me call this, I don't know, E1 and this E2 here. And because the diagram is so simple in this case, you could be a little confused. You actually have to draw the same diagram effectively inverted, flipped, because what happens is thinking of this as corresponding. So this is a subgroup lattice for Z6, and there's a corresponding subgroup lattice for the Galois group as well that would look exactly the same as this because they're isomorphic. And for example, the trivial one would just be epsilon in the Galois group. The fixed field of that trivial subgroup, just epsilon, is all of Q of A. So effectively, this gets matched with the bigger field as far as the fixed field. The highest one, all of the Galois group, fixes only Q itself. So effectively, the big group up here, the entire Galois group, goes with the bottom fixed field. So that's why I'm saying the diagram really gets inverted, but because it's such a simple diagram, it doesn't seem like it's inverted. And these middle things, if you think of them, the corresponding subgroups in the Galois group as being made up of automorphisms of Q of A that fix Q, will match with E1 and E2, although maybe I should do it the opposite there and there, just to remind myself that the flipping is goes on. And the 2's and the 3's get matched up as well. I guess this 2 would go here, this 3 would go here, this 2 would go here, and this 3 would go over here, technically speaking. And these numbers are degrees of the extensions related to dimensions of vector spaces. Anyway, the fact, as far as answering the question goes, the fact that we've got 4 subgroups of Z6, including the entire group and the trivial one, means we're going to have 4 subfields of QA extensions that are also extensions of Q containing those? The answer is 4. Okay? Okay, so just the basics of this stuff. This is, even though it seems really hard for people, this is just the basics. You can get much harder than this. That's either inspiring or discouraging, depending on who you are, but I hope you enjoyed this video. Thanks for watching.